Welcome back. Today, our topic is data fundamentals for transport. I would like to introduce this. It's the second to last topic we will cover as part of our lecture series. Data is something very important that you all work with and will work with in your future careers. And the way I wanted to start is with this quote, and this is really the main takeaway from this presentation. That is, what gets measured gets managed. That's a famous saying in business, but it also applies really well to cities and transport. And when I say measured, it really refers to collection, so data collection. What gets collected gets managed, and managed really refers to analyzed and processed. This applies to transport, but it can apply to your daily lives. If you want to run a marathon, you should probably start training, and you should measure your training and slowly improve each and every week if you want to manage your training properly to get you to being able to run a marathon. This lecture here is our fourth. This is sort of the slide we've used, but it could have been organized like this, because data is not a standalone topic. It's an overarching topic. If you work in NMT, you need data. If you work in electric mobility, you need data. Transit-oriented development, you need data. You need data for everything. Data sits on top, and there's lots of different data sets that you need to use. And you also measure this data in different ways, and you manage it in different ways. And we'll cover some of that today. And the plan is really to first discuss the learning outcomes. I have 5 key learning outcomes from today's lecture. Then we will cover some of the fundamentals. So what data is, why it's important, some of the emerging trends, and some of the challenges and opportunities of working with data in emerging cities. And I'll explain what all of this is. And then we will look at how we use data in the different transport-related disciplines. So when I say disciplines, I mean planning. That's one discipline that some of you may work with, or you may become planners in the future. Some of you may become engineers. It's a different discipline. Some of you may become transport operators. And all of these different disciplines or professions require different kinds of data. The learning outcomes, the first one is just a broad understanding of transport data in the context of emerging cities. We've spoken a lot about emerging cities and what they are, essentially cities that are growing very rapidly, like Phnom Penh and many of the cities in the region. And I would like you to understand the different types of data, the different disciplines, which we just discussed, some of the data measurement methods, so how we collect data, then how we manage data, and then lastly, I don't think we'll have time, but how to govern data, and also the topic of big data and open data is very interesting and very relevant. And the next learning outcome is for you to understand some of the key terminologies in data. We have 2 big differentiations. One is historical data. Does anyone know what that is? And I know some of you have worked with historical data. When we went and did traffic counts in Takmao, you collected data on a Saturday in September, and you manually counted all the different vehicles. And now we have a data set for that Saturday in September, which is now in the past. So it's historical data. It's data of a specific event in the past. Now it is still relevant because not too much time has passed, but in 3 years, the traffic condition will be different. So that's historical data. The other kind of data is real time. As part of our project, we are installing cameras in Chbarampov. These are smart cameras that can count vehicles, and we get that information through a server on a computer in real time. So our traffic counts are coming in instantly. It's constantly updating. We call this updating on a rolling horizon. That's real time. Historical is data from the past. We collect data in different ways. And there's, again, two differentiations, and we'll look at examples of both. We have traditional methods, and I can use the exact same examples. A traditional method is using a clicker like this and a survey form where we count the number of vehicles. That's cheap, it's easy to do. That's how we've done it for many decades. And that gives us traffic counts. But now we also have more advanced hardware and software. You can see these two guys are installing the camera. And this camera is an innovative method to collect this data. Traditional methods have advantages. Innovative methods also have advantages. So here we don't need a big survey team. We just have a camera that collects the data. But obviously a camera is a lot more expensive to purchase and install. Then the other learning outcome is the difference between supply and demand data. You are part economists, so I'm sure you're familiar with supply and demand. And we previously discussed how your job is basically to absorb growth. That's what you will do in your career. You live in a growing economy, and you have to find ways to absorb this growth in the real world. And that all depends on the supply of infrastructure versus the demand. And your job is to supply more than, or at least enough transport infrastructure and services, like public transport, than there is demand for these. Because if you don't supply enough infrastructure for the demand, what do you get? You get congestion, exactly. Or overcrowding. Your public transport, your bus will have too many people if you don't have enough demand. And supply and demand data is fundamental to a lot of what we will discuss today. And obviously supply and demand varies throughout the course of the day. Your supply is more fixed, but your demand changes around peak hours. And you should find ways to minimize congestion, which generally happens in the peak hours. And we'll revisit this later on. But the main idea here is supply data. The supply is the infrastructure and the services that are available. And the demand is how these are used, how people use these to meet their transport needs. So supply and demand data. And then the last learning outcome, and we brought this up already, is just understanding the different transport-related disciplines and the type of data that they would use. There are transport planners who do transport planning. I myself studied transport planning, and a transport planner, he works at a very large scale. He will develop plans, policies, strategies for all of Phnom Penh, and he works on a long time horizon. So your job is to plan for 2030 or 2050. And the transport planner can work with private transport, public transport, freight, and he has to work with a certain kind of data. And we'll look at what this data is, and that's the transport planner. Another discipline is engineering, and the engineer needs different data. He works at a different scale. If you work on an engineering project, it's much more detailed, and it's on a much shorter time horizon. Often, you will find an intersection with a problem, say Camco, for example. There's congestion buildup, there's accidents, and you go to the engineer and you say, hey, we need to solve this problem. The engineer will look at it, analyze the situation, and he will find a solution. So maybe he will reconfigure the roads so vehicles flow better or there's less accidents, or maybe he will reprogram the traffic lights so there's better flow. And that's the job of the traffic engineer, and he needs a different kind of data. And we'll look at what that looks like today. And we also have street designers. We won't cover this today, but we spoke about this 2 weeks ago in the NMT lecture. And a street designer, he's interested in also supply and demand data. So for supply, he wants to know maybe the width and the length of the footpaths. And he also wants to know demand information, so demand data, maybe on how people use the footpaths or how many cyclists he sees. And then lastly, we also have transport operations. We haven't talked about this yet. We'll talk about it today. And a transport operator is essentially someone who works in these James Bond looking rooms. You have one in PPCH. It's basically a room with lots of screens where you can monitor the network performance in real time because it uses real-time data. So a planner, an engineer, a designer works with historical data. An operator, he needs real-time data. And we'll look at where this comes from, but some of you already might know, you said it earlier, it comes from ITS, Intelligent Transport Systems. The different disciplines use different tools, and we'll look at some of them today. We'll talk briefly about modeling and simulation, and we can also look at what we call Advanced Traffic Management Systems, ATMS, for transport operators. But now I'd like us to dive into the very fundamentals of transport data. And my first question to you is, what is data? Again, I always have very broad questions, but if anyone has an answer, I invite you to share. Yeah, all information that we know and have collected, pretty much. I mean, there's no right or wrong answer, but data can be facts, it can be statistics, it can be information. Data is absolutely everywhere. I have a phone. My phone has a gyrometer or something inside that counts my footsteps, and I can check and see that I walked, say, 2,000 steps today. That's raw data. It's information I can get from my phone, but it's not useful information until I do some processing. So if I write down Conrad walked 2,000 steps on the 22nd of November, then it becomes more useful information. But data is essentially, it's the foundation of information and knowledge, and it's the basis for decision making. We're all surrounded by data all the time, whether we think about it or not. And there's two main differentiations when we look at the highest level, the types of data. And I'm sure you've come across this before, but on one side we have quantitative data. That's numerical data. Something like how wide a road is. So if I say the footpath is 230 centimeters wide, that's numerical data. It's a measurement. While we also have qualitative data. That's data that's not numerical. And you would get qualitative data from, say, an interview with someone. If I speak to you and ask you questions, you give me feedback, that would be qualitative data. And you would probably share your perceptions, your attitudes, maybe share information on your behavior. And so qualitative data would maybe be, my experience of the footpath is good. That's data. It's not numerical, so it's qualitative data. And we have to collect all of this data. We have to measure it, because what gets measured gets managed. So step one is collecting the raw data. And you know this already, we have traditional methods and innovative methods, and we also have historical and real-time data. And once you've collected data, that's when the fun starts. It's when we start to manage the data, and that has its own workflow in itself. So if you do traffic counts, you count lots of data for, say, a 12-hour period. You have lots of survey forms, and now you need to bring them into your computer, into an Excel spreadsheet, for example. And step one is to clean the data. You might have made errors. There are numbers that don't make sense. So you either fix them or remove them. And maybe you counted all your traffic counts in, say, 5-minute intervals, but you want 15-minute intervals. Then you would aggregate your data. And once you've done that, you can start visualizing your data. And I have a visualization of Manila. It's traffic counts shown in 15-minute intervals, and there's also speed data. And when vehicles are no longer moving fast, it's an indication of congestion, and it's been visualized using different colors. So red means congestion, blue means light traffic. And if you look at this map, you can see peak hour. It gets very red, very congested around in the morning hours, so around probably 8, yeah, right around now. Very high congestion, and also in the evening, you can see peak hour congestion. And you can use this data to understand how traffic flows, but also to identify hotspots. So where is it really bad? You can see different areas in the city, and those are generally the areas where you would want to intervene with new public transport infrastructure or an improvement to the traffic signals. And that would happen in the data analysis phase, where you would do mapping and modeling, but also forecasting. So we know what's happening in real time. Now we want to test and evaluate potential interventions. So what if I add a new bus corridor here? How will that change congestion? Or what if I build a new overpass? What impact will that have? And that is all done in the data analysis phase, and we'll look at that in a few slides' time. Why do we use data? I mean, one answer we've already covered. What gets measured gets managed. That's why we use data. But any other ideas?
How the traffic would be in the future.
Yeah, to make predictions.
Yes.
Yeah, and that you need data to make informed decisions. Perfect. I have a more abstract explanation, and that's because our cities are more and more multimodal. In your lifetime even, you've seen more non-motorized transport, more personal transport, more shared mobility services. There's PASAPs everywhere in Phnom Penh now. There's more public transport. Cambodia will receive another 1,000 buses from Korea soon. There's more freight transport, also food deliveries, and more utility vehicles. So there's an increasingly multimodal transport system, which is adding to the complexity of the urban operations. We also have more and more infrastructure. Last month, the new bridge opened from Konorea to Kopik, and there's lots of plans for overpasses. There's plans in the more distant future about rail-based projects. You have new public transport stops emerging. There's talk of the new airport. Well, more than talk, there's a new airport being built, so there's more and more infrastructure being built. And there's also a lot of events happening. We have really two kinds of events. We have unplanned events, and events are things that affect the transport network. So if an accident happens, it has an impact on the transport network. If there's a flood, people have to drive around the flooded area, or they have to drive slower, so traffic moves differently. If there's a significant change to fuel costs, people will adapt their behavior. And these are all unplanned events that affect the transport network. But we also have planned events. But another planned event could be construction, or a concert, or last year, or this year even, we had the Southeast Asia Games. And there was a bit of a panic before the games, because we needed strategies to move all the athletes to all the different venues as well as the tourists. And we also needed the city to keep functioning. And I think to manage traffic, they went so far as or they proposed to even close schools, so there'd be fewer vehicles on the street, so the Southeast Asia Games would operate and run smoother. And all these different activities and infrastructures are competing through time and for very limited space. And yes, Phnom Penh is growing outwards, but a lot of the growth is vertical. We're building upwards. So there's more and more activity happening in the same amount of space, and that adds to the complexity. And this is just for illustration purposes. Where you can see the multimodality. It's very complex. Layer on all the different infrastructures. It should probably be the other way around. And then you have all these different planned and unplanned events. And when you look at it like that, it's really a miracle that anything works, because cities and transport systems are extremely complex. And for that, we need to find comfort in complexity. And data is really key to doing that. To derive valuable insights, to inform decision-making, and to optimize and improve operations. And this is especially important in emerging cities. In Europe, things don't change that much. Our cities are old, and we don't have the same challenge of absorbing growth. And like we discussed in the first lecture, you will have way more interesting careers, but also much more challenging. And an emerging city, I think it's worth just defining this, is essentially a city that experiences rapid economic and population growth. And sometimes the growth is so fast that the city's institutional and resource capacity to formally absorb the growth fails. It's growing faster than we can absorb, and that can create many transport, housing, and social infrastructure deficits. If the formal economy can't absorb the growth, then the informal economy will grow. And you see a lot of informality in Cambodian cities. You have a lot of informal transport. So a lot of the Khmer remorques, for example, work informally. The street vendors work informally. Many businesses work informally, which is not a problem, but it does create a dual economic structure where you have the formal economy and the informal economy. And the issue with the informal economy is we have no data on it. And this is called a data gap. And so we want to measure and manage how our city works, but we don't have the data that we need. And that's one of the big challenges of working in an emerging city. And this is the experience in many different cities, especially in Asia. There's so much growth. It's a very exciting time. But with that, of course, we have a lot of challenges. And the challenges that we experience in the transport world is traffic congestion, providing public transport. The city is growing so fast, you have traffic congestion, and then we need to build big infrastructure projects that make the congestion even worse. So it's very challenging, it's very expensive and disruptive. We also have a lot of informal transport, which don't have fixed stops or stations. They don't have timetables. It's harder to plan your trip using them, but they're everywhere here, so it's very convenient. And they're not subsidized, which is a good thing. The government isn't paying them to exist like they might have to do for the formal bus. So informal transport is great, but it does have its problems. And we also have a lot of what we call peri-urbanization. So Phnom Penh has a master plan that's designed to absorb the growth, but sometimes it fails to do so. And you have a lot of urbanization happening outside the master plan, and this is often illegal urbanization because people need somewhere to live, and if houses aren't being built or they aren't affordable, you will develop informal settlements. And that's very common in many emerging cities. And a big challenge is bridging this gap, which requires different methods. And the way we fill this gap is by digitizing and digitalizing these informal services. So creating data that hasn't previously been collected. And in Phnom Penh, we did a project to do exactly that. We wanted to understand all public transport in and around Phnom Penh and the neighboring provinces. And we worked with a company who specializes in this, and we did it with MPWT. And we wanted to get a picture of the real transport services in the city. This is just an illustration from Mexico City. This is the formal network, so the buses that the city operates and manages. But this is the real network. All the informal services that exist were not previously documented. And so if you don't have this information, you don't know where people are going to and from, and it makes it very hard to plan your city. So they went out and they collected all of this data. And now if you want to plan a bus corridor, you have a much better idea of where people are going to and from. Just so you know, this kind of data is stored as GTFS data. I don't know if you've come across this before, but any map-based application will probably be based off this specification. It's just a way of organizing your data so that you can import it and visualize it in different applications. And we wanted to do this same exercise for Phnom Penh. We looked at the minibus services, the coaches, the public buses, the Khmer remorques. So we wanted to understand how they operate, as well as the ferries and the train. And we wanted all this information to see how we can improve the movement of people and goods in the city. And so we set out and went to all the different termini, where all these different services leave from, which we first had to identify. And we interviewed them. We asked them how often they go, where they go, how much they cost. We got all of this information and we started mapping all the services in Phnom Penh. These are the city bus routes, which we knew already, but we found all the minivan routes, which were previously not known. No one had aggregated all the information. And we also did this at a provincial level and also identified lots of different stops that were never acknowledged as stops. So if you take one of the minivans to Kampot or anywhere, you stop along the way at different food stops, and that was never properly documented. So we wanted to document all of that to understand, to measure, so that we could then manage and develop new ideas. And in the case of Phnom Penh, one idea we wanted was to create one hub for all transport services. So now if you want to go to the provinces, you might use, Kim Sen Express, or you have Larita, or you have Vibol Express. So there's many different minibus operators, and they all work independently. They all leave from their own little business, and it's not the most efficient way to provide transport. It's as if every airline had its own airport in the city. It wouldn't make sense. And that's sort of the situation we have here. And me as a user, I don't care which company I use. I just want to use the best service that meets my needs. And it doesn't matter if it's Vibol Express or Larita, etc. I just want to go to one station, buy a ticket, and then whatever operator takes me to my destination doesn't matter, as long as the service quality is acceptable. So we needed data like this to explore ideas like that, to create new transit hubs in Phnom Penh. There's also a lot of opportunities in emerging cities. You will see this written. 90% of all data was generated in the last 2 years. Everything is becoming digitized. We have more and more digitized systems and services producing more and more data, and we also have a bigger diversity of data sets. And this is all evolving with advancements in digitization, cloud computing, processing power, and I'm sure you've experienced that in your lifetime. Even smartphones, every 2 years, they get so much more powerful. And there's also a lot of other innovations in open and big data, AI, especially in the last year even, IoT, so the Internet of Things, the different sensors. So much is happening in the world of technology, and it's affecting the transport sector in a very big way. And it's creating increasingly rich data environments. We have more data than ever before, but unless we can find good ways to process it and analyze it, it's not very useful. And to make it useful, we need good governance around data, which is a whole topic in itself that we won't go into today. We need legal and technical frameworks. Having access to data gives you a lot of power in some instances, and we need to manage that carefully. And we also need financing mechanisms to collect and maintain important data sets. And if we can do that, we can create many benefits. We can make more complex decisions. We can automate processes. We can increase efficiencies and just improve operations. So it's a very exciting time and challenging time. And I work a lot in what we call emerging cities, where there's less technology being used today, but that's a very good thing, because in a context of continuous technological advancements, less is more, because technology is improving so fast that if you invested in your traffic light system 10 years ago, you would get something with much less processing power. Whereas today, things have improved exponentially. And you might have heard of Moore's Law, where every 2 years, processing power doubles. And so there's huge advancements in technology, but at the same time, costs of technology are also going down. And that's Wright's Law, where every time you double the amount of units you produce, you see a 20% reduction in costs. So these are general rules, but basically in Phnom Penh, if you want to get new technology, you can get more advanced solutions today at a much better cost. And so you can develop a very technologically advanced city and set of transport systems and subsystems. So that was just the fundamentals. I think we'll look at one of the disciplines and then we can take a little break. And the first discipline is transport planning. So transport planners work with a certain kind of data. We spoke about this earlier. Transport planner works at a very large scale, and they develop plans and policies, and they view the city as one big dynamic environmental, economic, and social system. And you develop master plans, and your job is really to measure the current demand and also from that anticipate the future demand. And if you can do that, you can manage the supply of new infrastructures and services, and this requires working with a lot of historical data. So some of you may become transport planners in the future, and you will work with lots of different types of data. We'll look at some examples. There are hundreds, and we don't have time, but the main types of data to do transport planning include land use data, so data on the different zones in your city. You might have residential zones, commercial zones, retail zones, industrial zones. You also have different boundaries created by the different government entities. These are administrative areas, which you're familiar with in Phnom Penh. You have Tulkork, BKK1, TPP, etc. You also have land use information like points of interest, parks, waterways, etc. And you also have socioeconomic data that is very necessary for planning. So data on demographics, income, employment, education, etc. And this is supply data that you would need as a transport planner. And you get this from lots of different sources. You can get it from different government agencies. So MPWT collects a lot of data, packages it, and some of it is accessible, some of it is not. If you work for MPWT, you can probably easily access it for whatever plan you're developing. There's lots of GIS databases. There's census data. So every few years, a census is conducted to collect general information on the socioeconomic environment of Cambodian cities and provinces. You have also open data platforms. If you Google online a kind of data you're looking for, maybe you will find a data set online that's available to you. Or you can use sometimes satellite imagery, or do surveys yourself to collect this data. And that's sort of the base data you would need to start building up a picture, but we are working with transport planning. And to do transport planning, we need a lot of supply data on, say, the road network or the rail network, or if you have ferries, which we do in Phnom Penh, you need information on the waterways, on the non-motorized transport environment, where we have cycle lanes, where we have bus routes. So we need a lot of transport network data, which we can collect from different sources. If you want to create your own transport network, you can, using a GIS tool. You can use QGIS, it's an open source tool, and you could draw your own network if you wanted to. But you could also just download it from OpenStreetMaps. I don't know if you've come across OSM. You basically have maps from all over the world that you can download, and depending on the location, you have a lot of useful information. You'll know which is a national road, a primary road, a secondary road, and this is available and it's open source. Or if you want something more detailed, you can buy your map from different companies, data brokers who sell maps. So lots of different sources to get your transport network data. This is your public transport data. Again, different sources. You can find all your public transport routes and stops from different online platforms that have GTFS data. So previously we mentioned GTFS, and you can find different portals online where you can download GTFS data. There isn't any for Phnom Penh because that was only recently generated through our project, and it isn't open in the public domain at the moment. Or if you need transit data, you can buy it. So there's lots of different sources. Generally, there's a manual way to add in the data, say on your map, or you can find it online for free, or you can buy it if it doesn't exist. So there's lots of different options, and that's our supply data. Then we need our demand data. And all of this will start making sense in a few slides when I show you how all of this comes together. But once we have an idea of all the supply, all the infrastructure, all the services, we now need to understand how people use these infrastructures and services. And for that, we need population density data. And you get population density in different ways. You have traditional methods. So you can do a census, go knock on people's doors in a household survey and ask them how many people live in this house. And if you do that with enough houses, you can extrapolate and get an idea of density. Or you can use administrative records and start to understand how many people live in the different provinces or districts. And that's a traditional way of doing it. Now there's also innovative ways to determine population density. You could, if you're doing it at a very high level, so this is all of Indonesia, you could determine population density using satellite imagery. Or we call this remote sensing, when you use satellites to infer certain informations. Or you can use, say, mobile phone data. We are all connected to a cellular mast somewhere, and a telecommunications company can probably see that right now there's a group of people in one cell, and they could know that there's a higher density of people, probably not here, where there's not enough of us, but if you looked at the cellular data on a map, you would know that at ASEAN 2, there's a lot of people. You can see the density, and you can see that change over time. Imagine ASEAN 2 is here, lots of mobile phone data, and this is in the morning, and then after work it gets busier, and you can see how people move from their cellular data. So that's an innovative way of getting this data, and more we use cell phone data. It's quite incredible. We all have a data generating device that has a lot of geospatial and personal information. And if we can harvest it ethically, we can use it in very interesting ways for planning. We don't just need population data. We want to know where people are going to and from. That's fundamental to transport, and that's called origin destination data. So OD data. You will guaranteed hear this again in the future. And that's basically how people move or where they go to and from. If we are up in the north of Phnom Penh, this is not Phnom Penh, but we can imagine it is. I did a trip from around BKK1, around Independence Monument, to the north, and that was my origin to my destination, and later today I will go back. So that's origin destination data, and that's very fundamental to transport planning. We want to know more than just where people are going to and from. Ideally, we want to know who they are, if they're male, if they're female, what age they are, what mode of transport they used, where they are going, why they are doing this trip, and when or how often they do this trip. And if we can get this information, we can really understand how people move through a transport network. And that is extremely valuable. And the traditional way we get this data is by doing household surveys or going to a bus stop and stopping someone and asking them all these different questions, which is not very practical. Some of you have done surveys with people on the street, and it works, but it's very labor intensive. In this case, you would want to ask them, if they're taking the bus, where is your home? Where are you going to take this bus to? How did you get to the bus stop? Did you walk? Did you get dropped off? Where are you going? What is your final destination? And also information, maybe how long is your trip? And you would have to ask a couple thousand people this information, and you can build up a picture of how people are moving in the city. And it works. You get a lot of good information, but you cannot survey everyone. It's not realistic to manually survey everyone. So it's not the best method. It has many limitations. It's expensive. It's labor intensive. Like I said, you need many different surveyors to make it happen. You can't sample everybody. The quality of answers will vary. There's also a temporal limitation. If you want to get your origin destination for all of Phnom Penh, it might take you 6 months to just collect the data. And then by the time you have the data, you've processed it, maybe another 6 months. The reality is no longer the same as what you collected in your data. So this is the method we've used for many decades now, and it's okay, but it has a lot of limitations. Now we have a lot more innovative methods to understand people's origin and destination. We won't go into too much details, but if you use a metro system, we don't have one in Phnom Penh, but you use a card. Sometimes it's a smart ticket or a bank card, and you will tap your card when you enter the bus and tap your card when you leave the bus to pay. And that generates data on where you got on, your origin, and your destination. So now we can use this kind of data for planning. We also use location service apps. So an example of that would be Grab or PassUp. And Grab and PassUp, they know your origin, and they know your destination. They know a lot about you. If we can get access to this data from Grab or PassUp, it's very valuable for planning. Sometimes these companies share the data, sometimes they don't. It depends on them. And we also have mobile phone data again. So this is a very interesting and very useful data source that we are only really starting to properly use now. And that's really good, because sometimes I don't take a Grab or PassUp from my house and I walk for 10 minutes and then I decide to take it. So it doesn't know exactly where I began my trip, it doesn't know my complete origin and destination, but my mobile phone is always on me and knows a lot about my trips. And they know it 24/7, every day. So they have very valuable data, which is also a little bit scary, I have to say. Also, these innovative methods, they have their limitations. So we won't go into all of them, but if you want to use a smart card for public transport, you need a lot of hardware. You need a lot of units, devices in every bus that you tap on and tap out of. For location service apps, if you want to understand people's origin and destination, I think it's the case in Cambodia that it's more the younger population who use Grab and PASAP. The older population, they will not use the app, they will just call the tuk-tuk or Khmer remorque, and so they will not generate data. So it's not a complete data set. Mobile phone data also has its weakness because you don't know exactly where people are going to and from. Normally, it's based off of cells, which are quite big. That will change once 5G is everywhere. Then Smart will know everything about us. But for now, with 4G, the cells are still quite big. So they can know when we move from here, say from here to here, they can detect that. If we move from here to here, they can't detect that because we're still connected to the same cellular mast. I don't fully understand it, but that's basically why it's a hexagonal shape and it's a cellular network, which is why in America we call these cell phones. We can get people's origin and destination, but we don't know if they went there by car or motorbike, so it's still not perfect. But we are getting better. You can use different kinds of algorithms. Say if you have a metro in a city, and you know the metro goes along here, and you see a high density of cell phone connections moving along here, you could assume that these are people in the metro. And with a lot of extrapolation, you can start to use this data to build up a good picture of people's origins and destinations and maybe their mode of transport. But obviously it's not perfect yet, and that kind of data will get a lot more detailed once we have 5G everywhere, which I assume is coming quite fast in Cambodia. And we spoke about the traditional methods and the innovative methods. Sometimes best practice is to mix both of the methods. So cell phone data, very useful, but has limitations. It's also not very personal. We don't get much personal information. So it's good sometimes to fuse it with a more traditional method where we also survey people, we get more qualitative data. And that is what I believe to be a better approach, to mix both traditional and innovative, and we can get a very good data set for planning purposes. We talked about a lot of different types of data. Now I just want to explain how we can bring all of this together for planning purposes using what we call macroscopic modeling tools. So macro means large scale, like macroeconomics, and we have macro transport modeling tools where we can create digital replicas, a digital twin of people's movement in a city. And we can do this for private, public, and freight transport. And you use these tools really to answer what-if questions. So you know your land use, you know all your road networks, and you know the demand. So you know how people are moving through the city. And once you've done that, you can use tools to answer, what if I build a new road here? Or what if I make a change to the public transport network? Or maybe what if I build a new hospital somewhere or a new stadium? What impact will that have on the transport network? What if there's a certain demographic change? What if there's a change in mobility prices? Or what if we introduce new regulations where a certain kind of heavy vehicle is no longer allowed in the city center? We want to use tools that can help us answer some of these big, complicated questions. And for that, there's different options, and all of them have their different strengths and weaknesses. And basically how these work is there's really 4 main pillars. These tools work as a kind of data hub, like a GIS. And when we say data hub, it's really a tool where you store all your data in one geospatial environment. So you will have your land use data, your transport network, your public transport network on a map, and you will have a very good picture of the real world in a digital environment. And that is your data hub. And you want to have a very good data hub for your city, because when you have that, you can do a lot of interesting analysis. So this is just an example. Here we can see the different zones, the administrative areas. So we could have this for Phnom Penh with all the different districts. And we have the roads. So you can click on any of these roads. We call them links. A link is a road, and you can see information about the road. So it's not just a map, it's very detailed. There's a lot of attribute information. We can see it has 3 lanes, it has a name, it has a code, an ID, it has a capacity, so how many vehicles can move through this link in a 1-hour period of time, for example. And we have a lot of information stored in our data hub. We also have a time dimension where we know the density of people in the different zones, and we know their origin and destination. And this is how we present origin-destination data. It's in a matrix. It looks more complicated than it is, but basically, this is zone 190, this is zone 10, and we can see 4 people moved from here to there in a certain period of time. And we understand exactly how people move from zone to zone, and it looks a bit like this. This is an example of a city in Germany, and there's 2 universities here, and you can see a lot of people moving in these areas. So the students live around here, and they go to the university, and the thickness indicates the volume, which is good. We see roughly where people are going to and from, but this isn't assigned to the transport network. This is just movement between zones. So this is not very useful yet. But once we have a good data hub, we have all our data, including our origin and destination data, we can start to do interesting analysis. And that is called running an assignment. We know where people are going to and from, between zones, but now we have to assign them to the transport network. And then when we run the assignment, we get something like this. We can see the volume of people in our transport network. In orange, we have private transport, and in blue we have public transport, and we can see where there is the most volume on the network. And you can visualize this in different ways. If you have the capacity and speed information, you can do a capacity analysis and see where you might have congestion building up. We looked at maps like this before, but with that you can start to see locations that aren't performing very well, or you can measure delays or get an idea of the level of service. And that gives you an idea of how your transport network performs. But your job as the planner is to not just identify the problems, it's to solve them. That's done by forecasting. So say this is your city, you can see a lot of vehicles are moving through the city center, but maybe not all vehicles are stopping in the city center. Maybe they want to pass through the city and go to a different destination. But right now, there's no good infrastructure to help you bypass the city. And if you have a data hub in your city and you know where people are going to and from, very quickly you can test different ideas. Why don't we build a road here to bypass the city? In the tool, in a couple minutes, you just click, draw your road, enter the number of lanes you want, indicate what speed they can drive at. You get an idea of capacity, and then you run a new assignment with your hypothetical, your new road, your intervention. You want to see how your solution performs. And then you run the assignment, you can see traffic reassigned to this road, because we knew that some vehicles coming from this zone were going there. They reassigned here and they don't go through the city anymore. And if we go back, we can see we've shifted some of the demand from this road over to this road. And with this new road, we will have reduced congestion passing through the city. And once you know roughly how much congestion you can shift, and you know how long and how wide your road needs to be, you can do a lot of interesting economic analysis. You can determine how much this will cost, how much congestion reduction it will contribute to, and you can also get useful information for your civil engineers. So that's how we can use these tools for forecasting. And they can also do a lot of interesting work with public transport. Say again, this is your city. you want to introduce a new public transport corridor, you basically just draw that in or add a new route or increase the schedule, the frequency of bus, and you want to understand how that affects the volume of passengers moving through your network. And you can do all of that in these tools. You could use the tool to identify the best corridor for a bus rapid transit system, for example, because you know where people are going to and from. You would want to put it somewhere where there's a high density of trips, and you can draw that in. You can also do your schedule. In this example, you can see at 6:45 in the morning from Stadium Station, the bus leaves. It's not very busy, but then from Central Station to Market Square, between maybe 6:50 and 7, there's a lot of people on the bus. And if you see this, it's very busy. You may want to add another service sometime between 6:45 and 7. And you can do all of this and test it all in this tool, which is a lot quicker and a lot cheaper and more practical than doing it in the real world. So modeling tools are extremely valuable for that. You can do a lot of interesting analysis on accessibility from different places or from bus stops. It's very valuable for a city to have some kind of macroscopic model. We spoke about the transport planning discipline. Now we want to look at data for the traffic engineering discipline. So again, different disciplines use different data sets. There are a lot of overlaps, and generally a traffic engineer will work downstream from the transport planner. The transport planner will create the master plan, but then you need an engineer to develop the more detailed components. So maybe the intersections. In this lecture anyway, when we talk about traffic engineering, we think of it in a multimodal context where we have different kinds of vehicles, but also pedestrians. So a traffic engineer doesn't just look at the movement of cars, but of all moving things. And the job of a traffic engineer is to optimize the movement of people and goods, including public, private, and non-motorized transport, with the goal of improving flow and also increasing road safety. We spoke about this in the first week. Good practice would be that the transport engineer focuses on moving the greatest number of people and not vehicles. Like that, it helps us think more about how we can develop public transport infrastructures which can move many more people than cars. And a traffic engineer does different kinds of work. His job might be to do a traffic impact assessment. So if you build a new ASEAN mall somewhere, that will have an impact on the road network. And before you build the mall, you should understand that so you can adapt your infrastructure accordingly. So that's something a traffic engineer would do. In Phnom Penh, there's a lot of discussions happening around different intersections, including the one in Tak Mau, in Tulkork. And for that, traffic engineers are being asked to explore solutions to improve flow and safety. Traffic engineer will also work on public transport systems. The job won't be to find where to put the corridor, but instead will be how to design the corridor once the planner has found the best location. The engineer will have to design it in more detail. And also the engineering of interchange hubs, where people go, say, from bus to tuk-tuk. There's ways we can design that space and make it as smooth, safe, and seamless for the users of the different transport services. And again, your traffic engineer will work with different kinds of supply data and demand data. For supply, very similar to the planner, you need to have an understanding of your road network. But the engineer needs more detail. He needs detailed information on the intersection layout, the number of lanes, but also how wide they are. So he wants to know if it's 250 centimeters or 280 centimeters. It's much more detailed. He would also want information on what vehicles can use the roads. Not all roads are to be used by different vehicles. Maybe information on your traffic lights. You want to know what the traffic signal phases are, how many seconds are green, how many seconds are red, and that changes throughout the day. So you want to know the signal phasing timings and also how they work. There's different types of traffic lights, which we won't go into today. And you might also want public transport data. So that's really your supply data. On the demand side, again, origin destination data is useful. This will be not really from zone to zone, but if you have an intersection, you want to know where someone enters and where they leave the intersection. And you can also have a kind of matrix for that. You want to know driving behavior, vehicle speeds. You would want to know your vehicle composition. You would have to do a traffic count, but you would want to know the different types of vehicles. How many are two-wheelers? How many are light vehicles? How many are SUVs or heavy goods vehicles? So that's your vehicle composition. You want to know turning movements. So how many are going, say at an intersection, how many go straight, how many turn left, how many turn right? And you may want to also know your public transport demand. So how many people are waiting at a bus stop or you riding a bus. So again, supply and demand data for traffic engineering includes these data sets, but there's many, many more. And once you've collected this data, once you've measured it, you can bring it into a different kind of tool. So we looked at macro, large-scale tools. Now we'll look at microscopic tools. And these are not modeling tools, but simulation tools. And the main difference, the macroscopic tool, you had roads, the links, and all your information is stored in the links. In a microscopic tools, it's agent-based. Each person, each vehicle is an individual autonomous agent, and they all generate their own data and behave in a certain way. So it's a different type of tool, and it's much more detailed, and it operates, from the data produced through agents. And essentially you can create a digital replica of what you see in the real world, and you can use this to test, appraise, evaluate, and visualize different interventions. And we'll look at some examples. And what's nice with these tools, not all of them, but some of them, you can also get nice visual outputs to communicate your engineering intervention. And they have lots of different applications. You can use them to optimize your traffic signals at a junction. You could use them to design your public transport, your bus stops and how the bus pulls in. You could design a car park, or add in a bike lane and see what impact that has on traffic. And you can do all of this in a simulated environment, which is advantageous to doing it in the real world, obviously. And we use these tools for many different purposes. So we explained some of them, and I'll give you a few examples. But first, the general workflow you would use to make best use of these tools. So say we have an intersection in Phnom Penh, and we see that there's several problems with this intersection. So if someone comes to you and says, let's fix this, you sit down and you have to develop a vision. And your vision is normally high level. We want to improve traffic flow, reduce congestion, increase safety, and make it maybe a more beautiful space. So that could be our vision. Then we would also want to develop key performance indicators. So maybe that could be reduce congestion by 10%. And once we have our vision, we can start working together as engineers and designers to create an improved space. And the first step is to build a base simulation or a base model. You use these words interchangeably, but it's really a base simulation. And a base simulation is a simulation of exactly what you see today. And for that, you need to collect data. So in Takmao, we counted all the vehicles for a certain hour in the day, and that serves as the basis for building a simulation. We then build our simulation, and the final step is to calibrate it, which is the process of making sure that the data you collected and the model you built reflects reality, which is easier said than done. We could do a whole lecture on calibration, because obviously in different countries, people drive differently, and you need to adapt your simulation to the local driving behavior. And once you have your base model and it closely reflects reality, you can start developing different scenarios. So say you have a big intersection, maybe you want to turn it into a roundabout. You design it in the solution, you test it, you see how it performs. So that could be your first scenario. You want to test another idea. Maybe we have some kind of footbridge and we program our traffic lights in a certain way and we close this street and it's more beautiful, but maybe it's not as good for traffic flow, but we want to test it and see how it performs. And then we have a final scenario where we create some kind of elevated park. It's super expensive, but it's nice. And in this hypothetical city, we have a big budget. So if we really like scenario C, we can test it and evaluate it and compare it to the base simulation and to all the different scenarios, and then pick whichever one best meets our vision. If we like scenario C the most, we will select it, and then we can go on to the next phase in the project workflow, and that would be a detailed design phase. And what's quite neat and nice with these simulation solutions, they are built off very robust and scientifically valid algorithms, but we can also get these nice 3D outputs. And if you want to, say, pitch an idea to the mayor of a city, and you come with a 200-page report, he will not be as excited than if you bring him maybe a 50-page report and a really nice video. This is really quite convincing. And you can even share this on social media and get feedback from people. So these are really nice tools because they give you some very sound technical analysis, but you can also create these nice visual outputs. And the way these work, we talked a little bit about how behavior is different. So in Cambodia, people drive, I wouldn't say people are aggressive, but they drive more aggressively. People can drive very close to one another. You have a very short bumper-to-bumper distance in vehicles, and sometimes you have very narrow lateral distances. In Germany, people, they stay away from each other. It's a different driving behavior. And if we build a simulation, we need to adapt it to Cambodia. Otherwise, it won't be realistic. And if the simulation is not realistic, it's not valid. And there are ways we can do that. This is an example of a simulation adapted to an Indian city. And in India, like Cambodia, people don't obey the traffic lanes. We go wherever we see space. And so if a motorbike here sees that there's a gap big enough for the motorbike, he will take that gap. That's the case in most emerging cities. And so our simulations need to be able to do that. And fortunately, they can. And so when we calibrate our model, we have to calibrate, we call it the Wiedemann car following model. It's basically an algorithm that can be customized to reflect whatever context we are working in. But the main idea is that cars don't drive at constant distances from one another. They get closer and further away, and there's algorithms to reflect that. It's good, not all tools are as customizable, but this particular one, with some good research on how people drive, you could build a realistic simulation for an intersection in Phnom Penh. I also want to share a use case. Does anyone know where this is?
No.
It's a very old photograph. of a famous place in a European city. So this is London, big city, 10 million people, and this is arguably the heart of the city. This is right in the middle. And this is about 100 years ago. And you can see here, it's called Trafalgar Square. It's basically a big roundabout, or it used to be. There's something like 4 lanes here, 3 lanes here, 2 lanes here. It used to operate as a big roundabout 100 years ago in a city that was much smaller, had a much smaller population, way fewer vehicles, and this was how traffic moved. And if this got congested, you would get congestion in the city, but 100 years ago, only rich people had cars. This is it today. So it's hard to see, but do you notice any differences? So what do you notice here? It's a pedestrian walkway. This is no longer a roundabout. Instead, they have a small roundabout here. This was done as part of a UNESCO project. UNESCO values historical places. This place has a lot of history, like Angkor Wat. And they received money to improve this space because it's very touristy. And before it was like an island of pollution, and they wanted to improve it. And so now it connects to, I think there's a museum here, and they improved this public space. But to do that, they had to shift the roundabout here. They went from a very big roundabout that could handle a lot more capacity down to a much smaller roundabout in a city that is now 10 times bigger, has 10 times more cars. So how did they do that? How do you reduce the amount of road space without causing a lot of congestion? For that, they had to test a lot of different options, and to prove that the option they chose worked, this small roundabout, they developed a simulation. And basically, this is an ITS project. They developed what we call a queue relocation strategy. Basically, there are intersections here, 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 and here. We have intersections at the roundabout. And these traffic lights are demand responsive. There are detectors in the street, and when the street here detects a 60% threshold, so when there's a buildup of 60%, they will send a signal to the traffic light up here to go red and hold traffic back. So this can never become overly congested. It's the same here, same here, same here, and same here. And by holding traffic back at the different intersections, they ensure that there's always good flow at this small roundabout. And yes, you can create some congestion upstream at the other intersections, but what's very critical is that that roundabout never gets too congested, because then the whole city center will feel it. It's a really interesting example of how you can use ITS and demand responsive traffic lights to make better use of your very limited capacity. And they proved that this could work in a simulated environment before, or to get it approved as a project. So quite a nice example of how you can use a simulation tool. And you can do many other types of analysis with these tools. You can look at speed, times, delays, volumes, and there's also ways you can determine vehicle emissions at different locations. And this is all great, but of course, the real world is extremely complex, as we discussed earlier, and it's too complex for mathematical models and algorithms to factor all the different variables. So models and simulations, at the end of the day, they're only approximations. It's near impossible to create something that is exactly like reality, but not using tools like this is much more risky than using a tool that's only an approximation. And that was very vehicle focused. There's also pedestrian simulation tools, and you have some traffic engineers that only work with pedestrian simulation softwares. And their job will be to maybe design public transport stations, and interchange hubs. And people also behave differently in different countries and cultures. If you go to maybe Japan, people like their personal space more than in Cambodia. And you have to calibrate your pedestrian simulation to that local behavior. This is based off the social force model. It's a different kind of algorithm which emulates how people walk. So if you walk in a tunnel, so imagine a tunnel. If you're by yourself, you will naturally walk in the middle. If you are with two people next to each other, you will like rearrange yourself accordingly. So there's an algorithm that's meant to reflect how people move naturally in the real world. And we can use this to assess capacity and level of service. So level of service is a way of showing how comfortable someone might be in a given infrastructure. If you're not in a busy place, your level of service might be A, if you can circulate freely. If you're in a very busy space and there's too many people and you can't properly walk, that would be a level of service F. And when we design infrastructures during peak hour, we should avoid F, probably avoid E, and worst case D, but aim for level C. And here's an example from a big interchange hub where people are leaving the trains, and you can see the level of service of pedestrians as they enter and leave the different boarding areas. And here you can see there's quite a buildup, a lower level of service here, but overall it seems quite okay. And this is quite useful. Say you want to build this infrastructure, you haven't built anything yet, your civil engineering team and your architect give you a design and you want to test and see how it performs before building anything. You do that, you see, oh, this is a bad level of service. You go back to the architect and you will say, okay, maybe we need the staircase to not be 3 meters, but to be 4 meters, or we find a different kind of solution. And so for big infrastructure projects, it's really important that we simulate how they will perform, because otherwise you can create, quite an unpleasant user experience. And if you don't enjoy your experience of the public transport system, maybe you won't use it. And we should always try to create the most comfortable and dignified transport services possible. You could also use it at an airport to know how many baggage checks you need, for example, for how people interchange from a tram to a car park. For, say, a stadium, when you have a big event, you can have 40,000 people in a given area at once, and that's something you need to manage very carefully. And also for building evacuations. So if there's a fire at the stadium, you want to know how long it will take for everybody to exit the stadium. And if it takes too long and it's too dangerous, then maybe you should design extra exits in your stadium. And all of that can be done with pedestrian simulation tools. So that's traffic engineering and some of the data and tools you might work with. And the last topic I wanted to introduce today is that of transport operations, which, as we discussed earlier, uses real-time data. And this is really quite different to what the planners and engineers do. They basically sit, monitor what's happening, and respond to any emergencies. And to do that, to know what's happening, they need to have a constant data feed of what's happening around the city in the different infrastructures and services. And that is made possible by intelligent transport systems, which feed what we call traffic control centers or traffic management centers or operational control centers. There's lots of different names used to describe roughly the same thing. And again, it's all about measuring real-time data so we can then manage it. And it's best we start with where the data comes from, how we measure, and we get that from intelligent transport systems. Does anyone know what ITS is, or anyone have an example? CCTV, yeah. We looked at one already in London that could be considered ITS, a demand responsive traffic light. Yeah, a smart traffic sign. So you could have a sign that gives you useful information. That's often called a VMS, a variable message sign, or a DMS, a dynamic message sign. ITS is just a whole other world of acronyms. There's hundreds and hundreds of ITS systems and services. Just so we break down the definition, the intelligent in ITS refers to hardware and software. Transport, we know what it is. We have different modes of transport, and all the different modes have different solutions, different ITS solutions. And systems in ITS often refers to subsystems. And when the subsystems come together, we create complete systems, and these are really ITS solutions. So ITS is quite broad in its definition, but generally an ITS solution is made up of systems and subsystems. So sometimes you have cameras, but the camera is only useful if it plugs into a software, and that software needs to be monitored by some controller somewhere, and only when it all comes together do we have an ITS solution that we can use to manage traffic. ITS, we could define it as real-time data measuring systems and services for optimizing the movement of people and goods. And ITS are, or can be described as automated monitoring and controlled systems that help us find comfort in increasing complexity. It's all about monitoring, seeing what is happening in real time, and when we can see what's happening, we can manage it, we can control it. If you see there's been a big accident somewhere, and you control the traffic lights, you can hold back traffic from the accident. And it's, again, ITS is made up of systems and subsystems. If you want to have an optimized public transport service made of buses, your buses can use lots of different technologies so that they operate as best as they can. And we'll look at some examples, but just to give you an idea that we can install technology, different hardware and software in our vehicles and around our cities for lots of different purposes. If our bus, for example, has some kind of telematics unit, a unit with a GPS, then we know where the bus is, which is useful as an operator. But you can also have a unit that communicates with traffic lights. And in a lot of BRT corridors, we create what we call bus priority signals. So basically, anytime a bus approaches the intersection, the traffic light will know a bus is approaching and will give it a green light. And that means that the bus will move through the network quite efficiently, which makes taking the bus maybe more competitive than driving your car. So that's a vehicle to infrastructure communication that you can have, which is really good. In many cities, you also have real-time passenger information. If you take a bus, it's nice to know when the bus is coming. In Phnom Penh, the bus has a schedule, but if there's very heavy congestion or if there's an accident, then the bus will not come on schedule. But if you have real-time passenger information, you will know when the bus will come, because this system will know where the bus is and can roughly determine how long it will take to reach the bus stop, which is nice as a passenger because you know how long you need to wait. And if you know how long you need to wait, you don't get stressed, you don't wonder, is the bus coming or not? And that's made possible with RTPI, and it gets displayed on these variable message signs like this. And this looks very simple, but there's a lot going on here to get this information. This is a data architecture. So all different ITS have different data architectures. And for this particular example, in the bus, we have a telematics unit with a GPS that links to a server, probably in the control room. And we know where the bus is relative to the bus stop. We probably have an idea of how much congestion there is. And with that, we can determine how long it will take the bus to get from where it is to the bus stop. And if there's a problem, this guy here, he can also write a little message on this board and say, the bus to the airport is late because of an accident, for example. And that goes through the server and then reaches the in-field piece of hardware, this sign. And so for this setup, you do need quite a set of different systems and services, but when it all comes together, it adds a lot of value to your public transport system. This is a more sophisticated kind of ITS. I don't know if any of you have been to Singapore. It's a very high-tech city. And I love this example. This is not new. They started this in 1998. And this is essentially what we call a gantry over the road. And it has an ERP system, which is an electronic road pricing system. Singapore is very small, and traffic was becoming a big problem in the 90s, and they wanted to reduce traffic. One way to reduce traffic, which is never very popular, is to make people pay to use the roads. The same way you have to pay to now drive to Sihanoukville if you use the toll road. Same concept, but they do this in the city. And it's automated. If you use the toll road, again, to go from Phnom Penh to Sihanoukville, you have to stop and pay with card or with cash, or you have an RFID tag that the system can read, but you do have to slow down. Whereas here, you don't slow down, you just keep driving, and the system communicates with your vehicle and takes your money. And gantries can host a lot of different ITS systems and solutions. The Singapore ERP system has RFID to read a device in vehicles, and I'll show you what that looks like. But you could also have cameras, ANPR cameras, which stands for Automatic Number Plate Recognition, where if your vehicle drives by, the camera will see your number plate and know who you are, and that could be included. And that's what we're doing in Phnom Penh with the project I shared earlier with our cameras that can count traffic. We can get number plate information, but we could also monitor the weather with a road weather information system, or speed radars, or air quality. There's lots of different ITS, and in some cities they build gantries and collect lots of useful data to monitor and manage. And in Singapore, every vehicle, every registered vehicle has this piece of machinery inside, and you have to top it up with a card, and you put money on the card, and then when you drive through the city, it takes your money away, which is annoying for drivers, but it means that the annoyed drivers can choose to take public transport if they want to save money. And the money generated from the ERP is used to cross-subsidized public transport. So it's part of Singapore's broader sustainable urban mobility strategy. And you can't really see it here, but the price you pay is also dynamic. During peak hour, it's more expensive, so you're less inclined to drive during peak hour, which makes the peak hour less congested. And you also pay a different price for different vehicle types. So trucks pay more than cars, and motorbikes pay less than cars. So it's using pricing to influence driving behavior. So it's quite an interesting setup. And this has been adopted in a few cities in the world, but Singapore is now doing away with all these, and they're just using connectivity to satellites now. So you don't need any of this hardware. You just connect to satellites, and you have an almost invisible ERP system, which they're currently phasing in. And Using this ITS, I don't have a year here. I should see if I can find the year, but they reduced peak hour traffic reduction by 25,000 vehicles. By also reducing the number of vehicles through pricing, they increased average speeds by 20%. There was a 13% reduction in overall traffic. And I tend to like this solution if and only if the money generated is used to finance high quality public transport. So these are all different kinds of ITS, and all the data generated has to come together somewhere. And generally it comes together in these traffic control rooms where you can manage your data in real time. And you'll see them called traffic management centers, operational control centers. They have lots of different names, and there's different types depending on what type of transport you are monitoring. And it gives you a top-down management perspective. So basically you get we call it a bird's eye view of everything that's happening in your network from one centralized location, which is very useful if you want to improve and optimize the flow of vehicles and also improve safety or best respond to accidents. From this room, you can monitor, you can watch and see what's happening. If you want, you can also control traffic on, say, a national road. If you see a lot of congestion is building up on National Road 1 in Chparampov, you could reduce the vehicle speeds, change the sign, and say instead of driving at 80 kilometers an hour before you reach Chparampov, you could say let's drive at 50 kilometers an hour, and so you'll reduce congestion. You could do the same with traffic lights, reconfigure your traffic lights to control how vehicles are moving through your network. In the control center, you also store lots of data. You collect so much data, you can store that for historical analysis, and you have lots of different softwares. So it's really like the brain for your city, or at least your transport system. Cities often have a traffic control center. So Phnom Penh has one in PPCA. Some cities also have a separate one for buses or for the metro, or even just for emergency services. The police often have a room where they have access to their cameras and they can see what's happening. And in some cities, you have what we call an enterprise OCC. And an enterprise control center would be one place that covers all of it in one location. And these are vital pieces of infrastructure. In some cities, they even have a backup control center. So if anything happens to this one, there's a fire, a terrorist attack, something, you can't just go offline, especially if you have a metro system. So you need to have a backup somewhere so you can quickly resume operations if anything goes wrong. And this is often what you would see. You have alerts coming in from different sources. It could be from the police. It could be from Twitter. You have an idea of how the road network is performing. And again, you can use different color schemes. So here, free flow speed, this looks good. You can see all your different cameras. Some of these are, we call them PTZ cameras. So pan, tilt, and zoom. So this guy, if he wants to see what's happening here, he can move the camera, control that. And if you see anything go wrong, if you see a red line appear here, you can find the closest camera and go to that location and see what's happening. And if you see there's been an accident, you can use your little phone, call the police or an ambulance, depending on what you need. So these are very useful infrastructures for cities to operate their traffic. And this is what they often look like. So you have a wall of screens. You have the different operators who work different shifts, day shifts, night shifts. You have spaces, if there's an emergency, you can group together and discuss potential strategies. You have all your servers, because you have so much data coming in, you have to store that somewhere. Yeah, that's the general setup of control rooms. And these are also improving. In the past, we would have CCTV cameras that would give you an image of what's happening. So you can see what's happening, which is useful. You might have speed sensors. So at different locations, you would have a sensor on the side of the road or in the road that gives you an idea of how fast a vehicle is driving. And you would have inductive loops. They're like rubber cables under the road, and every time a car drives over it, you can count a vehicle. And all these cameras, sensors, and loops in the street it's extremely expensive to put them everywhere in a city. But if you do it, you can better respond to accidents, and you have an idea of how traffic is moving in the city, which is good. But this requires a lot of hardware, super expensive. And most European cities are set up like this. Today, however, we have new technology and new methods. Instead of just having a camera that gives you a visual feed, you can have a camera that counts. You don't need loops anymore. Your camera will count. Your camera can also detect number plates. If you have number plates information, you know who's driving the vehicle, if your vehicle registry is up to date. And you can also train your cameras to categorize vehicles. So in our project in Chparampav, if a car drives by, we count it, but we also can detect if it's a tuk-tuk, van, a jeep. We've trained our camera using artificial intelligence to tell us what kind of vehicle it is. And then we can also use floating car data. So a lot of cars have GPS units, and Grab also generates floating car data. So we don't need sensors in the streets anymore. Our cars have built-in sensors. And if we can get this data, we can build up a picture of vehicle movements in our network without installing lots and lots of hardware. So a couple cameras and existing data from Grab or Google or someone who sells floating car data, we can do everything we can do with a lot of hardware and even more. And basically using these new methods with a lot less hardware and a lot more software, we can develop very advanced capabilities. And I think this is extremely exciting for cities like Phnom Penh, where you haven't invested tens of millions into developing these now traditional style advanced traffic management systems. Instead, you can use new methods and do a lot more with a lot less. One example of this is a project, one of the earlier projects that explored some of these new methods in the city of York. Not New York, but York is like the original city that New York got named after in the UK. It's a very old city, and you can't add more roads. You don't want to destroy the historical center. It looks nice. So they wanted to explore ways to make better use of the existing network. And they had to use ITS to do this. And they wanted to develop a traffic control system for the city, and they didn't have a big budget. So they developed a solution using, it's called PTV Optima. It's basically a fusion engine, and I'll explain more or less how it works, but it does everything that a traffic control center can do. Gives you an idea of how traffic is moving in real time in the city without all the sensors that you would need. So they already had traffic lights with cameras so they can detect demand, and they had some sensors in the city, but not much. And to build up a complete picture, the way they did it is they used their existing hardware that they already invested in a long time ago, and they fused it with floating car data. So I don't know if you know TomTom. TomTom is a company that aggregates floating car data from lots of different vehicles, and they sell this data and you can buy it. So this generates a lot of real-time data, and you can aggregate this data and start to really understand what's happening in real time. And then they layered it on top of a macroscopic model. So if you don't have real-time data for a specific location, you can look at your model that you would have built for your city for planning purposes, and where there's no data, you can assume what the traffic performance is because you have an up-to-date offline model in the background. So I don't know if that makes sense, but basically, to develop an advanced traffic management system, all they had to do was get floating car data, fuse all the existing data, and for a very low cost, they could develop very advanced capabilities. And I think it's, again, a really interesting time for you to be working in this space, because we're going through so many different revolutions in data science and electric mobility, and everything is coming together. And so I like this example because it shows us how we can automate data measurement and management. It also shows us how we can leverage all these different advancements in technology and data science to help us find comfort in increasing complexity. And this particular example, I think, is neat because it shows us how we don't need to spend so much on hardware anymore, because we have very powerful software and we have a lot of services that already generate the data, like Grab, like PassApp, like every car that has a GPS. The data already exists. We just have to find ways to harvest the data and fuse it. And this is great because it makes a lot of these solutions much more accessible for emerging cities. And at the same time, we can deliver increasingly advanced capabilities. So that's enough for today. We could do much more. We didn't talk about open data or big data or how to govern data. If that's something of interest, we can explore that in the future. Or something that would be fun is also looking at the simulation tool. If we can find an opportunity next year, we can do some trainings on how to use these tools. And I hope that through today's lecture, you have a more rounded understanding on where we can get the data we need to measure, so we can then manage using these different tools. So thank you for your attention. This was a lot of a lot of information condensed into 2 hours. Thanks for watching. SMMR is an ASEAN-German cooperation project implemented by GFA Consulting Group and partners on behalf of GIZ. For more information on the SMMR project, do consider checking out www.summer.asia. We look forward to seeing you there.